Hello, this is William from Visual Components. In this video, I'm going to show you examples of using mobile robots. This is helpful if you want to learn more about how the robots work, learn things you can do with them, and get some ideas for your own projects and solutions. This tutorial does require several layouts, which you can find a link to in the video description. So download those layouts, and what I did with those layouts is I put them in an examples folder, which I then put in my My Models folder so I can quickly access the layouts from my eCatalog panel. I've also turned off the Components filter, so I'm just seeing the layouts here. You can use Visual Components Essentials, Professional, or Premium. Some layouts do require access to the Modeling tab, which is listed here. But all I'm going to do is show you the code and explain what I did for certain cases, so if you are using Essentials, you can follow along. It's okay. For these layouts, we are going to do them in order. So here's the order. Move these back. For the first section, we're going to focus on how you can place parts on a mobile robot. For the next section, we're going to focus on how the mobile robot can carry items. And the last section, we're going to focus on using a collaborative robot or cobot or robot arm with a vehicle. So we're first going to study how we can retain the orientation of parts when they're being transported to and from a vehicle. We're then going to focus on how a human worker can place items on a mobile robot. We'll then get our introduction to using modules, something you can attach to the mobile robot. So a human worker will place parts in a box module. And then we'll see how the human worker can place things on a shelf or rack system that is attached to the robot. In the next section, we'll look at how you can implement a lifting module. So the mobile robot can lift things up and lower them down. Think of a Mir 500 robot that can, transport pallets. I'll then give you an example of using a hook system where the mobile robot can tug things. So they're not the same as carts. Tugging is a bit different, and that's why we are going to do an exercise about this topic as well. And the last layout in this section is a conveyor module. So you may have seen some cases online where you can have a flexible or movable conveyor system where you have a series of mobile robots that have conveyors attached to them. We're not going to do anything that crazy. We're going to have a simple conveyor module that allows you to transport parts to and from the vehicle. In the last section, we're going to be using a UR5 robot. So a simple case where the robot picks and places parts on a box that is on top of a mobile robot. We'll then use a robot module itself for picking and placing the parts. And whenever a robot arm or cobot is attached to your vehicle, you may want it to have a certain configuration or orientation while the vehicle's moving. So I'll give you an example of how you can use a Works robot controller and a RobotProcess task to define the configuration for the robot, and how you can implement a simple Python script to define the travel position for your cobot or robot arm. Sounds good? All right, let's get started. So the first one is about part orientation, so let's find that layout. Let's go here to my eCatalog panel, and I have the examples folder already selected, so that's what I'm searching here. Let's do orientation. And it's this layout here, so open in the 3D world. And we have two parts here. So we have a green triangle and a cylinder. We're going to be using the green triangle. So when we run the simulation, you can see this is the orientation of the part right now. And let's switch to the Move tool and use the Object Coordinate System. So this is the orientation of the part in its X, Y, and Z coordinates. And we want to retain the orientation of this part when it's being transferred to the vehicle. So the way I do that here, I'll stop it, is that the X, Y, and Z axis of our part, it is aligned with the X, Y, and Z of our pattern here that we have in our vehicle. So you can see they're aligned, so they're just moving down together. Then the vehicle will transport the part over here. And I did something a little bit different in this station. So the orientation the part has is still the same, it's just that we have a different location for storing the item here. And that is defined in a frame, which I teach to the process component here. You can see I have a location stored for any component that has a property of 111. And you can see the part is positioned at this location here. So this is defined as a frame, which you can see is at this location here. So if we want to edit the location of this part, let's use our Move tool. and rotate it along the z-axis -90. And if we want to save this location for our part, let's select our station and then use the Only Contain Components checkbox and click the Teach Location button here in the Component Properties panel. Notice it did not add an additional entry to the current locations property, it just updated the existing one for a component that has a priority of 111. So now the next time the vehicle comes to this station, let's speed up our simulation so we can see. Notice the part is now being transferred to that location, but its orientation is changing. So for a simple exercise, how can we have the orientation of the part to and from the vehicle stay the same at this process component? Well, let's take a look here. So let's stop our simulation and first find out what is the orientation of the station itself. So in its own coordinate system, you can see its x, y, and z axes is what direction they're pointing. And that is lined up with our parts, so that's fine. So it seems the only thing we have to change here is probably the resource location, or where the vehicle goes when it visits the station. So let's reset, select the process component, and in the Component Properties panel, let's go to the Resource Location tab here. And let's move the resource location to this side of the component. So angle location of 0. Take a look at the x, y, and z axis. You can see the y is pointing that way. We probably want it to be better aligned with these coordinate axes. So let's set the rotation to be 0. That's not what we want, so let's change that back to be, looks to be 180. Yeah, there we go. But remember the pattern element in our vehicle, it actually has a different orientation in the vehicle. You can see they're opposites. So with our vehicle, let's actually have it face this direction in the x-axis. So I'm going to change the rotation of that resource location back to 0. And because we're using simulation, we can quickly test. Let's see what happens. So all we did was we updated the location of storing the part and changed the resource location. And yeah, buddy, there we go. So now when the part leaves the vehicle to go to this station, you can see it's retaining its orientation. It's not, rotating around. So let's stop it right here. Slow it down. And if I select the part, you can see its x, y, and z axes are lined up with the pattern location here, which is also aligned with the frame or location where we're placing this part. And that's part orientation very quickly in a nutshell. So you can practice on your own further with this type of stuff. But let's move on to the next layout. So I'll press the Control and N key to clear the 3D world. And you don't need to save anything. So this is done. Let's put a giant X on it. There we go. Next layout is going to be focusing on how a human worker can place things on the robot. So let's find that layout. In our ECAT, I'm still in the examples folder. Human, and it's this layout here, human placing parts. One thing I did forget to mention at the start of the tutorial is that I'm using mostly mirror robots for these exercises and examples. You can, of course, switch them out for your own robots or use the generic AGVs we have in our library. Don't need to see these frames. And let's see what's happening here. So if we run our simulation, we can see a human worker is being used to pick up these cylinders and place them over here. So I positioned a works process component on top of the robot. So it's actually where the parts are being placed, and the robot can just stay at that location and grab them and then go to the destination where the parts are needed. We can see this in action. So once we get the needed pattern, the robot will grab the parts. Yep, and just move them on over here. And one thing to notice is that our vehicle is driving to and from the stations, and I position the stations in a way that the vehicle can go underneath them. So if we take a look, if we reset, the trick or tips and trick to make your vehicle go underneath the works process component, not to see it as an obstacle and avoid it, is to adjust the height of the component itself. So if I go back to the world coordinate system at this station here, go to its default tab, you can see its height right now, the component is 352 millimeters in the z-axis. I base this, of course, on the specifications for the Mir 100 robot. And if you check, its height offset property here is 0. So we're not elevating it above the floor with some offset here, we're elevating the component. But notice the resource location is at the bottom of the floor. So how is that possible? Well, if we go to the Resource Location tab here, you can see it can have its own height offset, which is the opposite or negative value of where I position the component. So you can see how their opposites are inverse of each other. So that's how the vehicle is able to drive underneath the station. And it's the exact same thing we did here for this component, where we're placing the parts and the vehicle is picking them up. So if you select the station, you can see it has that offset here, and the component is at that height, and the height offset for the actual component itself, or its detection area, is 0. Now a little bit more about the process. At this component, it's being told to create a cylinder and then feed those cylinders, and that has been assigned to a human. I just used a generic task name here of human, and you can see this worker has been assigned that task. Now these cylinders are needed over here. So we take a look at its tasks. It needs a pattern of cylinders, and we're placing them in a way which matches up with the location we want in the robot itself. We're then changing their ID to 111 because they're at a different stage in the production, and then we're merging them together. And the reason we're doing that is because we want to keep things simple. We're making a bundle of parts, so our robot technically only has to pick up one thing. And that's what we're feeding to the robot using this generic AGV task name here, which has been assigned to our robot. You can see in its task list. What we're then doing is running a human process task. So after the robot finishes delivering the items, it's told to come back to the station and wait for a certain period of time. So we're also using a generic task name here to have the robot perform that task. Now if we take a look at the robot's pattern, you can see it's fairly simple. It has the same height offset that we gave the station of 352. And we're only carrying one item, so this is where the bundle will be carried. And if we run the simulation, you can see that first part in the bundle is being placed there. So the other 3 parts will be merged with it, and that will be our location for picking things up. So if we wait until we get 4 parts, and stop the simulation. Yep. You can see with the PMP command, they're merged together to this component here, all 3 of them. So this is our bundle, which will then be picked up by the robot. Run the simulation. And yep, now it just carries them. Notice also that the human worker, when it's going here to place the parts, it's using a separate labor resource location component, not the resource location frame in the station here. Now you're probably asking at this point, how did the robot know to go back over here? Well, you can see that this component here is an idle location. So if the robot is not doing anything, it's being told to go back here automatically. And we position it at the same location as our station here. And remember, we're calling that human process task to bring the robot back to the station as well after it delivers the items. This is as far as I'm going to take this layout, because the other 2 layouts in this section are the same approach, just a little bit different layouts, a little bit different process that's going on. So I won't focus too much time on this right now. Let's clear the 3D world and go on to the next layout. So next one is a human worker placing things in a box module. Oh. So let's do a search for box in the examples folder. And it's this layout here. So box module with human placing parts. And if we look at the layout, it's the exact same layout we just had in the 3D world, with one difference. We have attached a box to the mobile robot. So it's very easy to attach and detach modules to the robot just by using the attach and detach commands you can see here in the hierarchy group. So all I did was add a box to the 3D world, resize it, and then attach it to the robot. So remember, if things are attached to the robot, they can move with it. We are also using a station here that was positioned to allow the robot to go underneath it, place the parts there, and make it easy to pick them up. We did, of course, adjust the height of the station for placing parts based on the thickness of the box. So if you select the station here, you can see its z-axis is not 352, it's 368, which is adjusting for the thickness of the box. And that was the same thing we did for the height offset for our resource location, so the robot can go underneath it. Once again, remember that the height offset we set for the component itself is 0. So now if we run the simulation, we'll see the same thing, but this time we'll see the box being carried with the robot, and the parts will be inside it. And here comes the last part. And here we go. Yep, so now the box moves with it and brings it over here. Okay, so if we were to detach the box from the robot, let's select it here, use the detach command, run the simulation again, and we'll speed it up. You can see that this time the box will not move with the robot. Yep, process still works, but we're not using this module anymore. So remember, if you want, you can just select a component and attach it to the robot. And now we'll move with it. So that's one approach. Let's clear our 3D world. We don't need to save. Go on to the next layout. Oops. Make this a bit bigger. And now we'll use a shelf module or rack system. So it's the same approach as before, just we're using a different module. And now we're going to be introducing the concept of you put things on the robot, but now you want to take them off. So let's search for that shelf module layout and load it into the 3D world. And this time the layout will look a bit differently. So let's look over here. And we have our shelf module, so you can see it's attached to the mobile robot. If we select the robot, you can see its pattern location here, so we adjusted that to be the height of the shelves in the module. The module itself comes from our ECAT, and you can see you can adjust its dimensions as well as the amount of shelves or racks in it. In the mobile robot, the pattern in this case is just being used as a visual aid for how we're placing the parts at the station that is listed here. So it still needs the cylinders, it's just that now it's using a different pattern. So it needs 4 on the Z-axis, and they're spaced 200 millimeters apart. And then we're feeding them. So with mobile robot, you can see I adjusted its pattern, location, and its amount. But the parts themselves, once we get them, we're still merging them to be one bundle and feeding that one part. So let's see how that works. So now the human is being told to pick and place the parts and placing them in this pattern. Then the parts are merged together and then put on the robot. So if we stop it here, remember these parts are being merged to this item here, the first location in our pattern in our vehicle. And then let's stop it here. And what's happening over here? We have a different worker that will unload the parts and put them on this buffer station here. Some process will execute, and then the human worker will be told to place them over here. Yep, once we get there, you can see it's driving to another station, and it needs that one part or bundle. It's then splitting up the bundle into separate components, and then we're changing the ID of the components to 222 because we're at a different stage in the production. We're then feeding those parts, and that will be handled by this human which we assign the task. You can see we used a task name of pick22, and that is assigned to its task list here. Now after we complete that process, we're using a delay here, so we don't want the vehicle to start moving away. And we're also using a sync task as well. So we're syncing this station with this station over here to let it know that the delivery was completed. The robot can go back here and wait for more parts. So let's see this in action. Yep. And now the vehicle goes back over here, and now it will be loaded with more parts. So a simple process. With the delay and sync task, you might have some questions, so I'll show you an example of how these can work to your benefit. Now, after we unload the vehicle, let's have a delay for about 10 seconds. So we're going to have the robot wait here for 10 seconds, then send the sync message back to the station that, hey, the robot is available. And then at this station, let's take a look. you can see after it feeds all the parts it has, it's then waiting for that, that notification, hey, the delivery was done. It's then calling the robot to come back to this station before it requests a need for more parts. So let's actually have the robot, once it gets back to this station, to wait another 10 seconds. So we're going to wait 10 seconds at this station before asking for more parts. And we're going to wait at this station 10 seconds after the human has unloaded the parts. So let's pay attention to the clock. Remember, that delay at this station will only happen when the robot gets back here after finishing its delivery. So once it gets the 4 parts, boom, it'll take off. The delay here is happening after we unload each part. So let's start counting. So around 10 seconds. Go back over here. And now we'll wait 10 seconds before the human worker can start loading it up again. So same approach as before in other layouts, just a little bit different of how we need to set up the pattern and loading and unloading the parts to the robot. Okay, what I recommend you do is test on your own with these layouts in this first section. Get familiar with how you transfer parts to and from the robot, how you can affect the orientation of the parts going to and from the robot to a station, and how you can use a box or shelf module. Let's now clear the 3D world. And we're done with this section and this final layout. Next section, we're going to focus on how we can carry things. So let's find that lifting module. So we'll do a search of lift in the examples folder and load this layout. Now at this stage, you probably would be helpful if you have access to the modeling tab, because this layout intentionally has one issue with its lifting mechanism. So you can see that I have a lifting module. Just like the box, it's been attached to the robot, so it will move with it. I've also adjusted the pattern location in the mobile robot to be where the part will be lifted from. So when we lift up the part, it'll be placed here. If we go to the component properties panel in the AGV tab here, you can see I adjust the height of the pattern location, and we only have one part that can be carried. And once the vehicle gets over here, we'll then pick up the part, but that was a bit too fast, William. Slow it down. So about 2 seconds. And what I'm going to do is actually save this as a view, or just create a quick view here so I don't have to keep on moving my mouse around. So the robot will go here, pick up the part, in this case lift it up, and then carry it all the way over here. Notice it's driving right into the station, and then drop it off here, lower it down. So let's add that as another view. Then once it's done with that, it will then go back and do more work. You can see it's going back. So let's quickly go back to that other view. You can pin the view editor if you want to keep this open, but I'll unpin it for now. But one thing I wanted to show you is that how this is working internally. So if I stop it right here, oops, right there, now front view, yeah. The part itself is not on top of this lifting section that we want for a robot. So you can imagine this is the bars, or whatever you want to call them, that are actually lifting the part up and lowering it down. So you can see it's floating right now, but it is at the pattern location. So in order to fix this issue, what we're going to do is go to our lifting module first. Then go to the modeling tab. Remember, if you don't have access to the modeling tab, it's okay, just follow along. And for its properties, you can see I'm controlling its dimensions. And I also used the I/O control tool here to quickly set up a signal that can trigger the lifting mechanism, either to lift it up or lower it down. We have a very simple joint that's in link 1. You can see the link itself, the joint is called J1. It has a min limit of 0 when the part is lowered down, and a max limit of 50 when we raise the part up. You, of course, can change these. And they're being controlled by a servo controller. In this case, an action signal is used to either raise up or lower down, and we have these state signals that can tell us, when it's in an up state and a down state. Whenever you have a joint in a component, it actually is added as a property. You can see J1 is here in the component properties panel, and right now it's at 0. For this feature, you can see its height is being manipulated based on the value of J1, so it has a height of 42 plus the value of J1 joint. But if I change the joint value, say to 50, it's not updating the geometry. So if you're in this type of situation, the way you can fix this is to quickly create a Python script. And what we're going to do is get that property of J1 in the component. So we'll first create a variable that gets the component that contains the script. We'll then get that property of J1. So use the component object to get a property. We have to find the property by name. Remember, it's called J1. And for the J1, we want to set this property. OnChange rebuild. I think it's called OnChange rebuild. You want to set this to be true. So whenever there's a change in this property, it will update the component's geometry. And I'm going to check my output panel. Nope, it's not named that. Let's go to our API real quick. So it's VC property. Yes, OnChange rebuild. Sorry. So we can copy this name and put it here. Press true. We didn't get an error in the output panel. That's good. Let's exit out of our script. And now, if we go back to link 1, keep your eye on this part of the module. Let's change the value of J1 to 50. And yep, you can see our geometry updates. And now, whenever we lift something up, this geometry will be updated to show that it's lifting the part and lowering it. Notice that it's not changing the pattern location that we defined in the vehicle. So with that, let's go back here and run our simulation. And yep, now we have that lifting module working. So it lifts it up, it's carrying it in the right way. Let's go back to that view we had. And now it should lower it down. And there you go. But you're probably asking, okay, so how did the vehicle know to do that? Well, let's take a look. So if we go back to our Home tab and use signals, you can see what I did is, to keep it simple, I added a signal in the robot that I'm using, this mobile robot, called lift down signal, lift up signal. And I connected them to the states of the vehicle here, so I can know when the lift is at its max height and when it's at its minimum height. Our action signal here is actually being triggered in a script that's in the robot. So if we exit out of the signals, go here, or did I actually implement it as a task? Now I'm trying to remember. No, we're just doing a basic feed. So select the mobile robot, and we'll go back to the modeling tab. And the heart of the mobile robot is going to be its brain script, which you can see here. So here are the signals that I added, and I showed you about the states, but we want to go to the brain script here. And it can seem like a lot, but I did leave you some note at the top about what's going on. So basically, when the notes or the comments have this text here, that allows you to quickly find what I did in this script. So it indicates when I modified the feed need transport task for the vehicle associated with the lifting module. So if we want, let's copy that text, paste it here, and then go down to find the next instance of it. Hey, here we go. I left some more notes here. So we're using a lifting module in the receive task. In this receive task method, we get the part we need and our lifting module. So we're going to use our lifting module to fill up these properties here. And then we'll get the container and grab the part. And here we're signaling the action to raise up the lift. So we need to receive a part, so we need to raise up the lift to lift it up, pick it up, I mean. And then we're using a trigger to wait until we get a notification that the lift is up and it's at its max value. Because then we know the part has been lifted up. You can think the pallet is now being carried by your vehicle. And then the other instance we can see here, for ship task, that's when we're placing the part. So we're using the module to unload the part. We're getting the values or the arguments from our lifting module again. This time we're signaling a false value for our action signal to lower the lift. And then we're waiting for the lift to be down and at its minimum value. These lift down and lift up. These are referring to the state signals that I mentioned here. So these states let us know when it's at its up or down state. And then you can see at the station that we were going to, that was actually passed in this method. We're using that to get a container that will then grab the part from our mobile robot. Let's continue down. Down, 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 down. And this is actually being called in the on-run event, if I remember. Let's see. I believe so, yes, but we'll see. So what we're doing here is we're trying to create a lifting module. So if the lifting module exists, this is a separate thing. We're using our lifting module if it exists, and then we're going to use that to ship a task or to place it. And then here, further down, you can see this is where it's checking if we have a lifting module. We'll then use it to get a part. And then further down here, it's the same situation, just a different task that's being called. And I believe we define our lifting module in the on-run event. Let's see. On start, no. Just going to quickly go through here. And yep, sorry, I should have updated the note here so you can quickly find it. So I'll do that now. Just add it here. Yep, so we can find it here, and what it's doing is we're actually creating a module, or in this case a tuple, that has set values for our lifter that's being used to lift up the part, our action signal that controls the action of the lifter, and those two signals that indicate when the lift is down or up. And that's what we're using to create that module. And that's what's happening here. So that's the script in a nutshell for the lifting module. You will see a similar approach in other layouts, so I'm not going to spend too much time here on this example. Let's now clear our 3D world. And I'm not going to save the change. And what you could also do is go back to your robot. Since we've already updated the module itself to use that J1 joint to rebuild geometry, you could delete that Python script we added earlier. And it should still work. But I won't save this. Let's now go back to our Home tab. And that's the first one done in this section. With the hook system, let's see about this one. So usually when a robot's using a hook system, it has to tug something. So the hook is being used to grab it, and then it's just holding on to it while the robot moves. So let's add the hook system layout. And I didn't do any coding at all for this layout. I strictly used the pattern, the resource location, and the pattern of the vehicle to get what I want. So this is just one approach. You could, of course, make your own scripts or other behaviors to get what you want. So with this mobile robot, you can see with its pattern, I moved it all the way over here. And that's an offset I added based on where I need to grab this rack here. So the rack, I actually fitted it with a tube here to cushion where the vehicle is grabbing it. And I also added a new component here that has a QR texture or QR marker to kind of simulate that, hey, the robot has to scan this and know it can pick up the part. That's actually not being used at all. It's just a visual tool here right now. Because all we did was move the pattern location and adjust the resource location at the station for picking up the cart. I did edit the dimensions of the cart a bit, this rack, you can see here. And I'm also using an approach location with this station for how the vehicle has to go here, back up and pick up the rack. And you can see that's what it's doing there. So no coding, just simple change the resource location, the pattern location, maybe use an approach location, and that's it. And let's speed it up. You can see I'm also using an approach location at this station as well. So the vehicle will go here, and now go here, turn around, and put it back there. I've already talked a bit about the approach location and these resource locations in previous videos, so I'm not going to spend too much time on it. But let's go ahead and go on to the exercise of how you can take a different approach than this. You can use the tug property of a mobile robot. So if you select the robot and go to its component properties AGV tab here, it has these two properties, tug ID list and tug distance. So whenever the robot is going to pick up something, you actually can put that product ID here, and the robot will know that it's not supposed to carry it on the pattern, it's supposed to carry it behind the robot or tug it like a cart or some buggy. You can also define how far away it has to tug the part. So that's different from using carts. So with carts, it's assumed that you're going to use the carts to carry other items, not the item itself. Not be the item itself that's being carried. So to see how that works, let's clear our 3D world. And let's go now to our exercise so we can mark this layout as being done. So now let's find the exercise layout. I'll do a search of exercise. Find an examples, and it's this layout here. Currently this layout is incomplete. We have to do work for it. It's an exercise. So what I'm going to tell you to do before showing you, what you could do to finish the exercise is that your task is to make this robot tug these cylinders. So you don't want to have the cylinder on this cart. You want it to be tugged behind the vehicle and not placed here. So if you want, you can pause the video, try to do it on your own, and then continue watching. So I'm going to first show you the approach of placing the part on the cart. I'll then show you the approach of tugging the cylinder and not using the cart at all. So remember, if you want to use the cart, select it, get its name, select your mobile robot, and you want to add that cart to its cart list here. So it's in the AGV tab, paste. You can define the distance between the mobile robot and the cart, and you can see now it's tugging away. And notice it's not using the cart to carry the cylinder, so what we can do is select our cart again, go to the default tab, and in our case we're not using a block, we're using a cylinder which has a product ID of 111. So if you add it to the part ID list, notice the part is now going on to the cart here, and that's what's being used to carry the item. I did show you in a previous video how you can use approach locations and change the resource location to better align the cart with the station. But let's just go on now. What I'm going to do is detach the cart from the vehicle. So I'll select the mobile robot, go to its AGV tab in the component properties, and clear out its carts list. And you can see now the cart is not being used and the part is going onto the vehicle. So if we stop it here, if we want to tug this part behind our robot, I know it's unrealistic, but it's just so you get an idea of how you can use the property and tug things. So the part itself, its name is cylinder, but its product ID is 111, and that's what the robot is being told to pick up. So instead of picking up the part and placing it at a location where the robot can carry it, let's select our robot, go to the Component Properties panel in the AGV tab, and for our tug ID list, let's add that product ID of 111. For tug distance, let's put it at, say, 500. Run the simulation. I'll slow it down. And yep, now the part is not at this pattern location. It's behind the vehicle. It's being tugged by it. So you can think of a tugboat. And remember, it's still carrying the part of where it needs to go. So if you don't want to use this location, what we could do is we can run the simulation again, speed it up, and let's stop it right here. If we make our vehicle invisible, let's now teach a location for this part at this station. So I'm going to snap it. Let's actually exit out of that. I'm going to turn on the frame for this resource location, makes it easier to pick. You can see there's the frame. Let's hide the geometry. The resource location, sorry. Go to this tab and clear out show location. Select our part again. Use the snap command, and let's snap to the frame here. Remember, our tug distance was 500, but I'm not quite sure of the dimensions of the vehicle. But we can quickly just demonstrate what you can do. Let's move it back along the x-axis to somewhere over here. So let's drag the x-axis. I think right about there is fine. And now to save this location, let's select our Works Process component, go to the Default tab in the Component Properties panel, and teach that location. Notice we have an issue here. The part is not yet in the station. So let's wait until it's there, stop the simulation, and now if we teach the location, you can see it is updated. But we lost where we had the part, so let's just redo real quick. Let's select the component, snap it, and put it to that frame, and then drag it along the x-axis in this direction. Right about there. Select the Works Process component, and click Teach Location, which will then mark or update that current location we had earlier. So now, if we run the simulation, the vehicle, oops, I made it invisible, so if you can't see it, what can you do? Well, just go to your cell graph panel, or don't listen to William. And you can quickly see that it's invisible from its category or its item, so we can just turn it back on like this. If it was hidden and you don't want to make it visible, you could just use the Show Hidden Components. You can see it there. But we do want to make it visible. Run the simulation, and we're still going to be tugging away that part, but now when we let go of it, it's going to that location there. And for our layout, we're done with the exercise. And now let's move on to the conveyor module with our mobile robots. So let's find that. And this is a bit more of an advanced layout. It might be, so you probably will need to take some time and kind of study and ask questions later on in the forum about how I did this. So what I did, if we look at the currently open collection in our eCatalog panel, I manually created a two-way conveyor, so a conveyor that allows parts to go in and out of it in either this direction or this direction. I also made some interfaces that allow the conveyor to connect to different ports, so it can connect in different ways based on where the parts need to flow in and out of the robot. Primarily the parts will flow in and out of this interface here. So the robot will go to this station, connect to its path, transfer the part in, get the notification from a sensor that detects the part is there, turn off the conveyor, have the robot start moving to where it needs to go to deliver the part. It will then get to that destination, connect to its path, transfer the part out the same way it came in, wait for the sensor and feedback that the part is now off the robot, and then go back and repeat the same work. So we have a two-way conveyor. We have a block that we're using to kind of simulate a box. We then have a conveyor sensor, which is connected to the two-way conveyor here. You can see. You can change its distance along the path. We have a robot, and that's about it. So the main thing for getting this to work is to use a Python script, and I've already talked a little bit about that approach with the lifting module. So now we're going to go into a bit more detail. So this is how it works off the gate. It's just transfer the part in. And you can see it's waiting for the part to be released, and then it gets the signal and it can go back over here. And let's stop the simulation here and actually make this a view. So notice the robot is not taking off. It has the part, but it's waiting for feedback from that signal. And it gets the feedback, so now it's moving. Let's stop the simulation here and make this a view as well. Robot's transferring out the part. It's still waiting. You can see the state of the vehicle updated as well. And now it's going over here. So how does that work? Let's take a look. So with our sensor, let's look at the signals real quick. Its sensor signal is connected to the robot, and what I did was add this signal here called part on conveyor signal. So the sensor is going to notify the robot of when it has a part and it is ready to move. With the lifting module, you can see it doesn't really have any signals. So let's take a look at this component here. It's attached to the robot, of course. The same thing is for the conveyor. It's attached to the block here. And the sensor is attached to the conveyor. So you have this type of hierarchy going on. If we now go to the modeling tab, let's look at its behaviors. Doesn't have any for the block, but for the conveyor, you can study this a bit more if you want to see how you could implement your own two-way path. And for our sensor, it's we didn't really change anything in the sensor. So the heart of the system is actually in the robot, and remember the robot, its brains is that Python script here. Let's take a look. And once again, I did document the sections that I've added, which you can quickly find them. So use this prefix here. Just copy it. And let's go down. So here we have the conveyor module that we're using to receive parts. So we have our conveyor module, and I probably made the same mistake earlier where I didn't put that right note at the start. It's here, yeah. So let's add that. I'll make sure to add that to the layouts that you'll get for this tutorial so you don't have to do this extra step. So now if we go back up to the top and start searching, we're going to call this method when we have to receive something on our robot. So we're going to use our conveyor module to get these arguments here for what we need. We need the conveyor that we're using, the path, the interface we're going to use to connect, as well as a signal. Now for that path, notice that it's a two-way path and we're changing its direction. So automatically it's set to go in reverse, but it depends on how the part enters the conveyor, it can change its direction. We're turning the path on. We're then getting the container at the station that has the part we need and its path. We're then getting its interface, and if that station has an interface that we can connect to, that was gotten from our conveyor module, we're then going to connect them, and if they can't connect, we're going to grab the part from the path. Oh, sorry, wait. This is a receive task. Yes, okay. So what we're doing here is we're grabbing the part to the station's path. So it actually is not in a static container, it's in a moving container, it's on a path. So because we connected the station's path to our conveyor, it will now flow onto it, and that's what's happening here. And then we're waiting for a trigger that from the sensor itself that the part is there. In this case, we're waiting for the sensor to reset to a false value. So first the part will trigger the sensor, then afterwards it'll reset it. We're then turning off the path to stop the part, and we're also turning off the station's path so it doesn't flow any more parts onto our robot. We're then disconnecting the station from the robot, so we're free to establish a new connection somewhere else. So sorry for the confusion early on about the code as well. But you can see the next step is to ship the part or to place it somewhere else. So our robot is going to deliver the part. Once again, it will get the conveyor module with these arguments. It will then change the direction of the path to now go forward auto. So by default, the path should go forward unless something comes in from a different direction. So now the part should flow out of the conveyor, and we'll get its interface and at the station we're going to and its path, and then we'll try to connect the interface at that station to our robot. And if they can establish a connection, we'll turn the station's path on as well as the robot's path, its conveyor module. We'll then wait to get a signal again that the part has left the robot, and then we'll have a small delay here, turn the path off, and disconnect the robot from the station. So that's how these two tasks work. And I think we should find something else here. Yep. So here's where we're creating the conveyor module. It's a similar approach to the lifting module, just we're getting different behaviors and things we need to make this module work. So we're first going to look for the items that we need, we need the interface, and we need a signal to know when the part is, get feedback of when the part is entered or left the module. And then we're creating our conveyor module based on this information here. So we're getting the conveyor, its path, which is here, as well as its interface for connecting to and from a station, and a signal in the robot that's used to monitor when the part has entered or left the conveyor. And I think that's the rest of this code. Yeah, these other items are just the same thing over again, but for a different type of tasks the vehicle might do for picking and placing things. So I won't talk too much about them, because you can see they're just calling those methods I talked about, ship task or receive task. Yeah, you can see here. Okay. So I hope by now you have a basic understanding of how you can use a Python script in the brains of your robot to create a custom type module, such as a lifting mechanism or a conveyor module, just by using simple codes and arguments for what is needed to make that system work. So if we run this again, you can see the paths are turned on. We wait for feedback from the signal, and then the paths are turned off, and the robot knows it can start moving. And once we get here, first thing we have to do is establish a connection between this robot and this station here, so you can see it's connected. You may have seen yellow arrows here, but this is referring to its two-way path, so this interface here is definitely connected to our conveyor module. The paths are turned on, so that's why the part can move from this conveyor onto this conveyor. And both the station and the robot are told not to move or do anything extra because we're waiting for that feedback from our sensor. So if we want, we can select our robot, go to the signals, and we can keep an eye on this wire here. Yep, it triggers. It probably was a bit too fast, but definitely the signal was received. And that's why the part flowed out of the conveyor here. Okay, I'm going to go ahead and clear the 3D world. You can practice on your own and study the code a bit more about how that layout works. Don't need to see the help file. Let's now move on to the final section about using a collaborative robot or robot arm. I did spend one entire video tutorial about using an arm, a robot arm, and how you can attach it to a robot, so I will go through some of these pretty quickly. But I'll spend more time on how you can do the robot process task and define a travel position. So the first one we need, let's go to our examples, was UR5, and it was UR5 and Box. Was that it? Yes, it was that one. So let's add this layout, UR5 with Box. You could switch this out very easily with another robot if you want. But it's just like in the tutorial earlier, it's just now we have a box that is attached to the robot, and we position our pattern to be inside the box. So now our robot, because it's attached to the vehicle, it moves with it, and will be used to pick and place parts. And that's it. So I'm not going to spend too much time on this layout. I think that's self-explanatory and was covered in detail. So I'm going to clear the 3D world. And now let's see the same approach, but this time with a module. So let's look for a robot module. Do a search, and here we go. And this is leading up to the other ones because you might be confused that if I have other things on the robot that are attached to it, will it be able to find this robot? Yes, it will, don't worry. So we can see we have this box here that acts as a module. It's attached to the robot. The robot is attached to the box here, the module itself. It's not attached directly to the robot. But because it is a child component in the mobile robots, hierarchy, it will be able to find it and use it to place parts. We also positioned a bin here, or a tote, or crate. You can call it a tray too, I don't know. Think of more words. And we position this and attach it to our module too. And for our vehicle, we edited its pattern to be inside that container, which you can see here in the AGV tab in the component properties. So we got the amount we wanted first, so 4 parts, and then changed their location and also changed their step size. So remember, as long as the robot is attached to the vehicle in its hierarchy, it doesn't have to be directly or an immediate child component, it can be used. So if we run our simulation, you can see the robot is being used to pick and place those parts. We didn't have to do any coding at all, mess around with any behaviors or component modeling. Just a matter of positioning the components and changing the pattern. And also making sure they're attached to each other. I also didn't use any special routes, I think, for this layout. Let me check real quick. So let's go here. Select this station. Yeah, I think I actually used a route in this case, because this is needing 1 part. And this is feeding everything. So if we select our Works Task Controller, go to Routes, open its editor. Yeah, we have a force route here called point AB. So we're going to pick whatever is available at the station, and then we have 4 place tasks here at the next station. And that route was assigned to our vehicle in its task list. Remember, we're not assigning it to the attached robot arm, we're assigning it to the vehicle. And because the robot is attached to the vehicle through its hierarchy, it can be used to pick and place those parts. Okay, let's go on to the next layout. So you can see how the first 2 layouts, they were a bit different. In this case, the robot was attached directly to the vehicle was attached directly to the vehicle. In this layout, the robot was attached to a module that was then attached to the vehicle. And now, when the robot is carrying items and it's traveling with the vehicle, you may want it to have a certain configuration. So one approach, you might have already thought of this, is can I use a Works robot controller with a robot that is attached to my vehicle? Yes, you can. Because we showed you earlier in this layout that as long as the robot is in the vehicle's hierarchy, it can find it and use it. So if we load that RobotProcess task layout example, this one here, UR5 executing RobotProcess, we can see that the Works robot controller is attached directly to the robot. The robot is connected to that robot controller. And because it's connected in a way that there's a hierarchy field here, it knows that the robot here, the vehicle, knows that it can use this robot. We have a simple pattern here of 1 part. So if we run the simulation, the vehicle will know it can use that robot to pick up that part and place it here. Now, one thing to mention is that the robot is now going to a certain position. And when we get over here, the robot will be used to place the part. And then it will go to that orientation before the vehicle starts going over here to pick up another part. So how did we do that? Well, if we go to our Works Process component here and access its tasks, we created a small delay, about 1.4 seconds after we feed the part. And then we're calling a robot process for a routine called travel. So if we select the Works robot controller, you can see that I assigned that task to this controller, which then assigns it to the robot that is attached to it. So the travel is the name of a routine I added to the program of the robot, which you can see here. And it's a very simple program. It has the robot go to kind of a home position, this point here, in its local coordinate system. So if we run the simulation, and yep, it goes to that location. So we might want to create a greater delay here, or where the need is needed, but it's fine. You can see the idea working here. It will pick it and then go to position 1. And now it's in a safe position to be carried by the vehicle back to pick up more parts. And that's it. So we didn't have to do any scripting, any coding at all. We just used the works library and the program editor here and the robot process task in this station. And in this station here. Let's clear the 3D world. And that's another layout. But if you want to implement your own logic for positioning the robot when the vehicle is moving, you can use this layout as an example to help you get started. So let's find it now in our Home tab. And load it into the 3D world. And the first thing we need to look at, is there any signals being used at all? Well, let's see. So there's no signal there. There's some inputs and outputs. Nothing being used there. So how is this working? Well, let's look at the tasks here. No, it's creating a cylinder and a feed. Just a simple. So what do you think is being done to make the robot have that right orientation or that right configuration? Oh, very smooth, huh? And go over here, and you'll see the same thing again. So this time you don't have to mess around with any extra tasks in the process components, add and attach a works robot controller. You're actually telling the robot what to do from the vehicle itself. So if we reset the simulation and select our mobile robot or vehicle, go to the modeling tab, what I did was edit the brains of this robot to call a routine in the robot whenever we're picking or placing something. So if we go to the behaviors and go to that brain script again, let's go and look for travel. I should probably add some notes here for you so you can quickly find it. I added this method. So define robot traveling. We're getting the robot that we're using. Remember, it's attached to it so we can find it. We're then calling this subroutine in the robot called travel. And let's find out, when is this method, robot traveling, being called? So we'll copy it and try to find it in the script. And I'm showing you this way of trying to find things because instead of me telling you where to go, you can learn how you can quickly find this stuff in the editor. So whenever we're placing something or unloading the vehicle, we're going to get the position, place the item, and then we're going to call this method, robot traveling, to put the robot in the right configuration before we start moving again. Then if we go down again, we can see when we're calling the pick method here to pick up something and carry it, we're calling that method again to have the robot get to the position it needs because the vehicle is about to travel somewhere. And that's all we're doing. So just a couple lines of code, very easy. And it's mostly being used when the robot is picking something or placing it. And now with the robot, if we go to the Program tab, you can see I define that routine here. So if we want, instead of going to this location, let's have the robot go, let's actually delete this position. Jog our robot and make it go all the way over here. Yeah, let's do that. Let's add a point-to-point motion. So this is how we want the vehicle to look when we're this is how we want the robot to look when we're moving the vehicle. To go when we pick something or we place it or when we're carrying it. So just a simple example and just one approach of how you can get the robot to look the way you want. And lean back. Oh yeah. All right. Let's clear the 3D world. And I think that's it for all the layouts. And Yep, that's it. So what you can do is you can go through these layouts again, try to learn more, practice on your own, and also ask questions in the forum because we can be helpful and respond really quickly to what type of things you're trying to do with the mobile robot. If there's anything in these layouts you didn't understand, you can of course ask questions about them as well. But this completes the video. If you have any more questions, please feel free to visit our forum at forum.visualcomponents.com. And as always, I hope you have a wonderful day.